This is the Marcellus Shale. This is what it looks like. This is what yields the gas. Don't try to light it. It won't light. I started giving these talks probably now close to 3 years ago. Sometime in that first year, somebody dropped a corn. And they actually did me a favor because, I'll pass these around. This is what the natural fracture tendency of the rock is. It's orthogonal, 90 degrees, and the rock breaks up. So the gas industry wants to take the rock that's like this, where the gas is locked inside, and break it up like this to get the gas out. Okay, so I'm going to talk about where in New York is the Marcellus and the Utica. How did they get to the gas resource? How did they get it out of the ground? And then finally, what are some of the water resource concerns? Obviously, a map of the United States. Marcellus is not the only shale gas unit in the United States. Marcellus is one of the latecomers. There's a large number of shale gas units across the United States. The Barnett Shale and the Haynesville Shale have been producing for at least a decade. Marcellus is fairly new. This is a gross exaggeration because this is the Marcellus in what's called Upper Devonian. It's not this large. Getting a little bit closer to home, this is a general configuration of the Marcellus. First of all, why is it called Marcellus? Because it was first described near the village of Marcellus, New York, which is south and west of Syracuse. Basically, you can see there's two different colors. To the west, the gas is basically undermature. It's a mixture of natural gas, what's called gas condensates, and oil. It's much more difficult to separate those products out. They are looking at developing this area here. The area in gray is much like I am. It's thermally mature. What that means is that, good, you're awake. Okay, what that means was a long, long time ago, that unit, which the Marcellus, when it was formed, was south of the equator, near the equator. It was a shallow inland sea, and a lot of vegetative material was settling to the bottom along with muds. And that's what created the Marcellus. Now, through the many, many millions of years, the Marcellus was pushed deep into the earth by other sediments on top. As it was pushed deep into the earth, it was put under a lot of pressure, and it was heated, so it was basically cooked. And then, the glaciers come through, we have less sediments on top. So over here, it's undermature. In most of this area, it is what's called thermally mature. It's almost just about pure natural gas. And the eastern extent, which may cover this county, it's overmature. There is no natural gas. I don't know whether you've heard that in northeastern Pennsylvania, I believe it's Wayne and one other county, the gas companies have sort of pulled out. They drilled wells and they found that they're not producing enough gas for it to be viable. Whether that's true here, I do not believe they drilled an exploratory well, in other words a vertical well here, in order to find that out. When these companies come in, they're going to do that first. They're going to test and they're going to see whether there's gas here. If there's no gas here, they're not going to develop here. This is from the SGEIS. This is the thickness of the Marcellus Shale. Western part of the state, it's about 25 feet thick. You go toward the center part of the state, it's about 100 to 150. You get over in here, it's over 300 feet thick. Now you notice there's no contours over here. There's no data. That's the thing we're lacking, is data over here to tell you whether it's thicker over here or it starts to thin on this side. So it's thick on the east, about 100 feet thick in the central part of the state, and very thin on the west. So if I would take a geologic section across the state, this is what it would look like. This is Erie County, Pennsylvania, and this is Otsego County, New York. This is where we have data. Again, it's fairly thin here, but as you can see, as we come east, it becomes much, much thicker. So people look at this, oh, they're going to drill lots of wells here. Not necessarily true. The upper part, oh, by the way, there are 3 units in the Marcellus. The upper is a shale, it's called the Owaka Creek. The lower is called the Union Springs, and there's a middle unit, it's called the Cherry Valley Limestone. In the Owaka Creek, the upper part of the Owaka Creek is a gray shale, doesn't have gas. So they're going to be producing from basically this dotted line, the lower part of the Owaka Creek, and just about all of the Union Springs. So even though it's thicker here, it doesn't mean there's more gas. Now, if you look at New York State from north to south, north being, let's say, Lake Ontario here, and this being the Pennsylvania-New York border, all of our bedrock that was originally laid down in flat-lying beds now gently dips to the south at the rate of about 40 or 50 feet per mile. So if this is the Jeffersonville Formation, and you go 1 mile to the south, hopefully I'm pointing south, and you go at the same elevation, it's going to be 40 to 50 feet deeper. Go to the north, 40 to 50 feet higher. So here's Marcellus, New York. It's where it crops out at land surface. And then as you go further and further to the south, it becomes deeper and deeper and deeper. This geologic section goes through the central part of the state. So at the Pennsylvania-New York border, it's about 3,000 to 4,000 feet deep. Why 3,000 to 4,000? If you're on the valley floor, it's 3,000 feet down. If you're on the ridge top, it's 4,000 feet down. So, general concept is the bedrock dipping to the south. The Utica Shale is on top of this blue unit here. It's not the blue unit. You can see that it's deeper. Whether it's thermally overmature, we don't know. They've only started drilling wells in the Utica in Ohio and western Pennsylvania, where in Ohio, it's oil. So they're going crazy in Ohio for Utica Shale because it's oil.
Meaning, what is that? I don't follow. What does that mean? They're going crazy?
They're drilling. They're drilling there. They're developing there. They're actually taking rigs from Pennsylvania because oil is worth more now.
Oh, I'm sorry. Okay, you mean the shale is not shale, it's oil over there.
The shale is shale, but what's in it is oil.
Oh, I see. Okay.
So again, dipping to the south, general structure of the bedrock. So if we look again from the SGEIS, this is where the Marcellus crops out at land surface here, down through here, and they have the general depth to the Marcellus. So in Sullivan County, you're looking at roughly 6,000 feet down. A little bit more, a little bit less. Is it overmature because it was pushed so deep into the earth? We don't know yet. So if you take all that information and you put it together, the gas companies develop what they call the play or the fairway. This Hatchard area here is the most likely area for shale gas development. It won't go up into this area here because it's too shallow. But from this, say roughly from this line south, this is the area of interest. Now, sitting in Albany, on somebody's desk in Albany, in the Division of Mineral Resources, there are 58 permits pending, waiting for the results of the SGEIS to drill horizontal wells in the southern tier. They basically go from western Delaware County through the Broome County, Tioga County, and Chemung County areas. I think that's next. No. The Utica Shale also follows the same type of development pattern. The Utica extends around the Adirondacks, is up in Quebec province, and extends all the way over into Ohio. We don't have a good characterization of it. The thickness and information we do have is generally showing that this will be the place. So the two plays sort of overlie each other. So if they drill a well pad for Marcellus, they may come back 10, 20, 30 years from now and drill deeper and go after the Utica because all the plumbing is already there. And when you see development, what you're going to see is you're going to see initial development where there's a natural gas pipeline. They don't want to build a pipeline over hill and dale. They want to drill where they can get the gas from their well pad right into the pipe. Okay, this is a stratigraphic column for New York State. This is all the bedrock. There's no quiz. Don't worry about it. But what's going on here, all these red arrows are indicative of black shales in New York State. We've got the Marcellus, and we've got the Utica down here, but we've got a whole bunch of other ones here. This Dunkirk one is really interesting. New York State's history gas well drilling goes back well over 150 years. The first gas well that was dug, it wasn't drilled, it was dug, was in 1821 in the village of Fredonia. They were digging a water well and they hit natural gas. They hit it in the Dunkirk Formation. They capped off that well, and what they ended up doing is they piped it and they lit the streets of Fredonia for about 50 years from that one well. Natural gas occurs in New York State. For roughly the last 150 years, the red and white Medina sandstones, generally the western part of the state, has been the gas producer. It's a sandstone. They can drill down into it. The sandstone has what's called permeability. You drill a hole into it, the gas will flow to the well. So for about 150 years, and still going on today, in the western part of the state, there's a well about every 40 acres. You go out there, people are just used to gas companies coming in and drilling wells. Those mineral rights were stolen a long time ago. Roughly in the 1930s, another sandstone layer started to be developed. It's called the Oriskany sandstone. The It's higher up in the formation, it's below the Marcellus. And what they did was they drilled those wells, and sometimes they got gas, sometimes they got brine, salty water, and sometimes they got a mixture. So what they'll do is if they find these features, they'll drill down, and then they'll drill horizontally, no hydrofracking, and they'll connect all those rooms. And if they have gas, it normally takes about a year or so to or more to pay off a gas well, depending on how much gas it produces. When they hit gas in the Trenton Black River, they pay it off in like 3 months. There's so much gas, but when that gas is depleted out of the room, there isn't any more. So the Trent Black River is a real quick player, where the Medina, Oriskany, and now the Marcellus and the Utica are longer-term players. You get a lot of gas initially, and then you get a long play of gas for decades. Now what's interesting is when they drill to any of these deeper units, they always had to go through the Marcellus. And the Marcellus, if you talk to gas well drillers even a decade ago, it was the bane of the gas well drilling. They didn't like drilling through it because they always had gas coming out. But the gas would come out for a couple of days, a couple of weeks, sometimes maybe even a couple of months. Then the gas would be depleted. I'll bring this. The gas would be depleted, and they'd move on. They'd seal off that section of the well and then go down to the target zone. They knew the gas was there, they didn't know how to get it out. That's where high volume hydrofracking comes in. This is the new technique to get it out. Okay, this is the map I was talking about. In DEC, there's not 58 dots here because there's multiple wells per these dots. But these are permits pending, waiting for the SGEIS to be passed. Southern Delaware County, a couple in Shenango County, several in Broome, a lot in Tioga, and a fair number in Chemung. Do you know why there's a heavy preponderance here? Northeastern Pennsylvania is a sweet spot for natural gas in the Marcellus in Pennsylvania. The gas doesn't look at borders. So they're thinking that they're going to do a lot of gas well drilling here to see if the Pennsylvania sweet spot actually extends into New York. These are ones that are pending right now. This is a picture up north, well up north here, that shows the 3 units, the Alaska Creek, the bottom part, which is a black shale, the Cherry Valley, which is a limestone, and then Union Springs, which is another black shale. This Cherry Valley is very important. When the drillers drill, they can actually detect this unit. And most times, the general consideration is they're going to put the horizontal leg down here, hydrofrac up into here, and hydrofrac down into Union Springs. So this is a unit that they can detect, and I'll explain that a little bit later. As I said, gas well drilling is not new in New York or Pennsylvania. These are thousands and thousands of dots for oil and gas wells in Pennsylvania, and the same in New York. The large preponderance of gas wells, western part of the state. We do have them in the southern tier. A lot of these are Oriskany. These are Queenston wells up here, and you'll notice not many dots in here. And again, that sweet spot in northeastern Pennsylvania is right here. Bradford County, Tioga County. Pennsylvania is another sweet spot down near the Pittsburgh area. All the way through here, there is Marcellus shale, but it doesn't seem to produce as much. One of the things I tell people about shale plays across the country, as well as the Marcellus, it's just like this audience right here. We're all human beings, but each one of us is different. So the Marcellus is different wherever you're going to be drilling. It could be really good back there and not very good here. And that change can be very subtle, or it can be very dramatic. When they drill and case a gas well, it's different than a water well. The water well driller comes in, he drills through the soil, he gets to the bedrock, he sets a casing. He should put cement at the bottom of the casing. Sometimes they do and sometimes they don't. Then they go in with a little bit smaller bit and they drill down through the bedrock. And they're looking for fractures. The old biblical saying, you don't get blood from a stone, you don't get water from the stone. You generally get water from fractures in the stone. So when they're drilling down, they're looking for fractures. And hopefully they find a lot of fractures up top. But sometimes they drill deeper looking for water, depending upon the units. That's a simple water well. A gas well is different. They use multiple casings and they grout the casings. They may start with a 30-inch or a 36-inch diameter hole. And they'll drill down through the soils and they'll drill down into the bedrock hundreds of feet. They'll stop. Generally when they get to the freshwater saltwater interface, they'll then put in like a 30-inch casing. And then they pump cement down through the inside of the pipe and then make the cement flow up the outside of the pipe all the way back up to the surface. What they're doing is they're trying to isolate the casing from the surrounding environment, and that's what the grout does. It basically separates the two. Does it always do a good job? No. But what they do is they do what's called a cement bond log, where they put a tool down the hole and they sort of look around and they look to see if there's any voids where the cement didn't fill. If it didn't, they'll go in and they'll perforate the casing and they'll do what's called a squeeze job. They'll squeeze cement into there. Once they're done there, let the cement set up, generally 12 to maybe 24 hours. Go in with a 24-inch diameter bit and drill down maybe several thousands of feet. And then stop, put in a 20-inch casing and do the same thing. Force cement through the pipe and fill up the annular space between the pipe and the drilled hole. And so what they're doing is they're putting several telescoping pieces of pipe down, isolating the well from the surrounding environment. So if this is a gas unit, let's say they were drilling into the Medina, and this is the Marcellus here, there would be several layers of casing and cement to isolate so this Marcellus gas doesn't come up the well. They get down to the production zone itself, and in the production zone they put a pipe in, cement it in place. Sometimes they don't run the cement all the way up, it depends on different rules, different states. Then they perforate the casing and then they get the gas to flow. This is the typical vertical type well. So this is a picture, this is sort of a series of illustrations where you've got pipe and you've got cement, another pipe with cement, another pipe that goes down into the clay, but here you've got some intermediate producing zones that they're not going to produce from, and so they've grouted them off. They've left this section of the hole open. This is what happened in Dimmick Township. There was a producing unit up here that got into this annular space, and you'll see this in just a minute. It filled this annular space and then came out and went into their aquifer. Pennsylvania had the old rule that they didn't have to cement this off. That rule changed after Dimmick Township. The New York rule, you cement them all. So, again, they're going to produce from down here. This is what they're going to produce. Here's the gas here. It's isolated. But if you don't get a good cement job, you don't get a good bond against the side of the wall, you can get gas that will start to move up. It can go up into this angular space here. Pressure builds up, and that can move into a shallower bedrock and into somebody's well. This is what happened at Dimmick. New York basically said, you cement them all. Will it be perfect? Nothing is ever perfect. In 1992, the generic environmental impact statement allowed for hydrofracking and allowed for horizontal drilling. When they started talking about the new type of high-volume hydrofracking, DEC said, this is completely different than the rules we had established before. That's why they came up with the supplementary generic environmental impact statement. Old way, drill a hole down, if this is the Marcellus, they were allowed to hydrofrac up to about 80,000 gallons. There's been reports that they've used more. I can't confirm those, but basically the rule was under the 1992, you could use up to 80,000 gallons of hydrofracking fluid to hydrofrac a vertical hole. The new way, you drill a vertical well, and about 500 feet from where you want the horizontal leg to be, you can then, they have a drill bit that basically cants off just a little bit, and in a 500-foot curve, it'll go from vertical to horizontal. And then they'll drill out horizontally. How far will they drill out? 3 factors. Number 1, what's the integrity of the formation? Is it solid like this, or is it already broken up? If it's already broken up, it's tougher to drill because you're going to have pieces falling in behind the drill bit, and they have to be very careful. Number 2, size matters. How big is that drill rig? How powerful is that drill rig that's going to be drilling that curve and horizontal leg? The standard in Pennsylvania is roughly 4,000 to 6,000 feet long. The longest one that I've heard of so far is over 12,000 feet, and that was drilled in Canada in a sandstone. So this leg will be between 4,000 to 6,000 feet long. And the final factor is the driller. The driller listens to his machine, uses the force, if you may. Basically, he looks at his dials, he listens to the rig, he listens to what's going on. And he knows, if he's an experienced driller, what that drill bit may be doing thousands of feet away from him. So those three factors will end up telling you how far out they drill. Once he drills, take the drill bits out and they put a casing in. And they cement the casing in place. So this leg has steel and has cement surrounding it. Sounds counterintuitive, but there's a reason for it. Once that casing is in and the grout is set, they go in with what's called a perforation tool. It's a series of pipes that have shape charges. Basically, they're about a $1/2 in size and about that thick. It's impregnated into the steel pipe. They set off these charges. These shape charges go through the steel, through the cement, and just into the formation. They create connection from inside the horizontal leg to the formation. And they do that along the length of the pipe. They take that tool out, and then they put in what's called a straddle packer. It's another series of pipes. It goes down the well, and it has like 2 steel balloons on it. And what they'll do is they'll go to the end of the pipe, and they'll inflate these steel balloons, and they'll inflate one here, and inflate one here. Then they start the hydrofracking process. Through that pipe down through here, they bring the hydrofrac fluid down to here, and then they start to pressurize. Now you heard it's thousands of PSI, and it's true. Because the first thing they need to do is they need to counterbalance the weight of all the rock above it. They have to get to the in situ pressure, so that's thousands of PSI. Once they get to that point, they very slowly start to increase the pressure. That's when the hydrofracking begins. They have to basically counterbalance the overburden pressure, and then slow incremental changes starts the hydrofracking process. And the hydrofracking is where these fractures move out. Now these fractures that they're creating are not fractures. The fractures that they're creating are paper-thin fractures. How do I know that? Because at several drill sites, I've been taking frac sand from the trucks. I'll pass this around. Look at the size of this material. This is going to tell you the size fractures that they're keeping open. This stuff is not going to keep open a large fracture. They're creating paper-thin fractures. Once they're done with that, they'll then pull the straddle packers back. They may put a plug here temporarily, and they do what's called another stage. So depending upon how many stages, these stages can be from 300 to 500 feet long, and they do them in series. The actual process of hydrofracking, once they get to the in situ pressure, is only about 20 minutes. It's not long, it's short. They don't want the fractures to go out of the pay zone. They want the fractures to stay where the gas is. They don't want to interconnect with another zone where there may be water, which would drown the well. Water is also the bane of a gas well. You got water in there, you got to pump it out, you got to do something with it. And that water is not Perrier. That is brine. 4 to 5 times as salty as seawater. It may have heavy metals, and in the case of the Marcellus, it has radioactive materials in it. And I'll explain that. Not all shale plays have radioactive materials. Again, each play is different. So Marcellus has sort of become the poster child. But if you go to the Bakken, you go to the Barnett, completely different water chemistry. Okay, how do they know where the fractures go? They do what's called microseismic. Now, the earthquake that was in Virginia, do you folks feel it here?
Yes.
You were like seismographs. You were feeling the earthquake. In Ithaca, there were people who were on the flats, which is a lot of sediment. They felt it. People who were up on the hilltops didn't feel it. People who were in tall buildings felt it. So what they're doing, in this case, is they're detecting these fractures. So what they do is they put a series of geophones either down a nearby well or run them on the surface. And as these fractures occur, it's like a snap, crackle, pop. And they can detect, because the difference in distances between each one of these, I mean this is milliseconds, they can detect where these fractures occur in 3 dimensions. And so by doing that, what they end up doing is they can map out where these fractures are going. So this is an industry diagram. Weatherford is what's called a service company. They do the hydrofracking. They don't do microseismic at every well. Generally, when they come into an area, they do it for X number of wells to get an idea of the characteristics of hydrofracking. Again, Marcellus here may be different than what it is right across the border in Pennsylvania. They need to know that. So this is a 6-stage hydrofrac. I put these ellipses on here to sort of give you a rough idea of what's going on. You see a lot, the first one's red, you see a lot of dots near the well, but you do see some fractures that are occurring further out. These are fractures a lot initially, and then they move out further and further. Each one of those is a crack. This is a plan view looking from above. Then they did the blue one, and the blue one is very similar in shape and size as the red one, and I'm sure some of the blue hydrofracts are related to the red hydrofracts. And that's why some of the blue dots are out a little bit further. Now you notice the next two, the green and the yellow. Different shape, different orientation. The rock is not the same every place. And then finally the last two are again completely different. So what they're trying to do is they're trying to shatter the rock either side of the horizontal hole to basically create a pathway for the gas. Now ideally the DEC and in Pennsylvania, the Pennsylvania DEP would like to see a number of wells coming off of one pad. They want to see, like, let's say this is the center of the pad, they want 3 or 4 going off in this direction and 3 or 4 going off in this direction. That way you have maybe 1 drill pad per square mile versus 1 drill pad per 40 acres. In doing so, there would be another horizontal here, they do the hydrofrac there, so what they end up doing is they end up rubblizing that zone. It basically creates the pathways for the gas to flow. So in this case, different ellipses, different orientations, different sizes, because the rock quality is variable. Just like us in here, human beings, each one of us is different. This is the result of, I'm not too sure how many hydrofracts down in the Barnett Shale in Texas. The blue lines up here are the depth of freshwater wells in the area where these hydrofracts took place. The red line here is the depth of the horizontal well. The excursions going up and down are the height, the vertical distances that these hydrofracts have occurred. Now we're going from hydrofracts from about 8,500 feet up to about 5,000 feet. You'll notice that some of these vertical hydrofracts are moving well over 1,000 feet vertically, up or down. But as we get shallower, the verticals become less prominent. And there's a reason for that. There's like a cone. As you get shallower, there's less overburden weight. Because there's less overburden weight, the stresses in the rock are such that the fractures will start to move out horizontally when it gets shallower. The deeper you are, the pressure is the weight of the rock, and the fractures propagate against that force. If they try to go horizontal, they can't because there's so much weight, it won't allow them to develop. But as they get shallower, the vertical fractures become less long. Poor English, sorry. They're not as long, they're going more horizontal. Now the interesting part in New York is we're looking at depths of hydrofracts anywhere from 2,000 feet to maybe about 4,000 to 5,000 feet. We don't have good data. One of our comments going back to New York State is to require the gas well drillers to do a lot of microseismic work so we see if this trend continues, that the fractures do move out horizontally and they don't move vertically. But this has been the story in the Barnett Shale. Also in the Barnett Shale, they have things called fractures and faults. And this was a test from the Voisier, I'm not good at French, but basically these are sandstones. The shales are the black units. They're looking for the tight sandstone units to have the gas. They did a hydrofrac in this unit down here, and they actually found some hydrofracts in the unit just above. They postulated that there was probably some type of fracture that allowed some of that fluid to move up into a higher zone. I do not know the distances here. I've been trying to find out, but I have not been successful. They did another hydrofrac, this orange here, and they found a lot of hydrofracts in these upper sandstone units. There probably was a fracture here that allowed some of the hydrofrac fluid here to move up and move out to these units. So fractures are of concern. New York State does not have a good fracture map. This is another point we're basically telling the DEC, is that we need better characterization. There are reports out there about fractures that they need to include. And as a well driller is drilling, sometimes they'll lose fluid flow. There's a fluid loss zone. If the well drillers would make notes on those and give those to the DEC, we might be able to take that data and basically be able to figure out where these fractures are. A smart gas company is going to tell the service company, don't hydrofrac near this water loss zone, because that means the fluid's going to go someplace they don't know. So if there's good communication, and if the gas company talks with the service company, they shouldn't be hydrofracking near active faults. We'll see what happens. Okay, 3 stages to drilling. If you've got a local well driller that's got a rig like this, he'll drill the vertical part of the hole. They'll hire a local well driller. Generally, it's drilled on air, just like they would drill your water well. What he'll do is he'll drill down. He'll keep going down until he gets to what is the turning point. He'll stop there with multiple casings, cementing in the casings. When he's done, he pulls off site. He's gone. He's gone to the next site. Then, stage 2 is basically the big rig. In this case, this is West Virginia. This is a big rig. This rig tower can be 150 feet high. It's so big that they don't drive it into the site. They bring it in on trailers, and like an erector set, they build it on site. They build it. They bring in all their equipment. This case, this is in West Virginia. This is their water source pond up here. This is the water they use for drilling, and the water that they use for the hydrofracking. This is the drill cuttings pond. Once they start to do the curve and the horizontal leg, air is not going to lift those chips up. So they create a drilling mud. It's a mud. And what that mud does, it's pumped down through the inside of the pipe to the drill bit where it cools the drill bit, and then that mud will carry the cuttings back up to the surface. They spill it into the pond here, the cuttings settle out. Those cuttings are like fingernail size. The cuttings settle out, the mud flows to this end, they pump it back down the hole. They recycle it and they reuse it. Once they're done with this cuttings pond, they'll generally drain it. The mud is hauled off someplace, or if they're going to drill more wells here, they'll keep it there. They may take the cuttings out, but then they'll reuse the mud. Depends how they drill the site. And then the water source pond is then available for the hydrofracking, which is done by a different company. The drilling company, the drill leaves the site, they bring in a service company. This is the Halliburtons, the Schlumbergers, the Weatherfords, there's about a dozen of them. These are the guys that come in with their own equipment, and they're the ones that do the hydrofracking. In this case, West Virginia, this is probably a vertical well. These are the water source here, a couple of large tankers, and these are what are called the frac tanks or the frac cans. You may see these going down the road. These are empty. They never transport fluids. They're there to be hauled to a site where they'll hold fluids. These trucks got real small tires on the back end. They're not meant for transport. They're just meant for storage. So in this case here, this is probably a vertical hydrofrac, a pilot well to try to understand what's going on at depth. This truck stop up here is like 130 of those frac tanks. I don't see a water source pond here, so initially they're probably all been filled with water. They'll do the hydrofrac, and then they will then be available for any water that comes back out of the hole. One of the biggest problems with this process is transportation. Getting things to the site and taking things from the site. You're looking at, let's say, 130 of these. You're looking at, I don't know how many tankers to fill all of these, and then you're going to have to haul this stuff back out. You're looking at hundreds of truckloads of going in and out, either up a road like this, or down Legion Road here, or a gravel road, to bring supplies to and take. Okay, where do you get the water for hydrofracking? There's 4 different potential sources. Initially, they'll go for municipal water. They'll go to municipalities that have excess capacity, and they say, we would like to buy your water. They like it because it's clean water. It's been disinfected, it's clean, doesn't have turbidity in it. They like that. In New York, I believe Binghamton, Owego, there's like 4 or 5 communities along the Susquehanna River that are presently selling water. That water is being transported from New York into Pennsylvania for hydrofracking. Another potential source is surface water. Surface water, streams. There are regulations in Pennsylvania and there are regulations in New York that you just don't pull up your truck, throw the hose in, and pump the stream dry. You're not allowed to do that. There are different rules in different parts of each state. The state has a set of rules, and depending upon what river basin you're in, there are different rules. The Susquehanna River Basin, which I will refer to as the SRBC, basically regulates the use of water. So, if you're in the Binghamton area, or if you're in Pennsylvania within the Susquehanna River Basin, the SRBC permits any water that's used for hydrofracking. Their old rule was if you use less than 100,000 gallons a day for 30 days, you didn't need a permit from the SRBC. When they started hydrofracking, the SRBC said, wait a minute, time out. First gallon you use, you need a permit from us. So in the Susquehanna Basin, they are regulated also by the DEP and the Susquehanna River Basin. You folks in the Delaware River Basin is starting to promulgate rules possibly similar to the SRBC on the use of water. Again, they don't want them coming to a little stream going past your house and pumping it dry. There are rules and regs that they're going to have to follow. They're going to have to get permits to remove that water. I live up in the Finger Lakes. Finger Lakes are not in the Susquehanna and they're not in the Delaware. They're in the Great Lakes Basin. All the Finger Lakes drain to the north. There's a Great Lakes Commission. It's an international commission, but they don't have people. They then rely upon the state. That's the DEC, Division of Water. And the Division of Water and DEC doesn't have people to do what the SRBC is doing. So there's a concern in the Finger Lakes, are they going to be regulated? New York State just passed a new rule. If you can take 100,000 gallons a day, send us a report once a year. That's not regulation. You folks are in the Delaware, you have a set of rules. Folks that live in the Susquehanna, you have a set of rules. The Finger Lakes, those rules aren't there. If you go to the Ohio River Basin, it's the Wild West down there. There's no rules, there's a commission, but they don't regulate withdrawals. It varies by where you are. So municipal water initially is the first one. As the gas company starts to become developed and starts to learn the rules, they then start moving towards surface water. Initially, in the Susquehanna Basin, it was about 60% municipal and about 35% surface water and just a little bit of groundwater. Now, it's about 70% surface water and about 30% municipal. They are taking a little bit of groundwater. As you know here, our wells don't yield that much water. So groundwater probably won't become a source. And then finally, there's interbasin transfer. Interbasin transfer from the Great Lakes to the Susquehanna, Susquehanna to Delaware, Delaware to Susquehanna. These basins have to agree to these transfers. So there are certain rules and regs depending upon which basin you're in. But these are the sources of the water. The quality of the frac water and the formation water. Again, an industry diagram. Most of what will go down the hole will be about 91% water, about 9% the sand or the propping agent to hold the fractures open. And then finally the witch's brew over here. This is not the proprietary chemistry. This is the chemistry you can probably find on any of their websites. This is not the recipe for Coke. This is the caramel, this is the water, and this is the carbonation. These are the general type of things. And depending upon whether it's a slick water hydrofrac or a gel hydrofrac will determine what chemistry is in here. There's a purpose for all these different things. A gel hydrofrac, just imagine I have a beaker of water here and I take a small beaker of sand and I dump it in. What happens to the sand? It settles to the bottom. Well, they want that sand to go up and out and down. So in some cases they'll gel the water. They'll turn it into sort of like an early gel. And that sand is supported in that gel material. So when that gel moves up into the fractures or down or out, the sand is being carried equally. When they do that, they have a gelling agent. They also have a little bit of chemistry, a cross-linker and a breaker. The cross-linker basically keeps the gel a gel for a certain period of time. And then the cross-linker breaks down naturally because the breaker wakes up and says, okay, time to go back to a liquid. Generally, that's after the hydrofrac, and they reduce the pressure, and so whatever's left over flows back out the hole, and it's not much. If it's not a gelled well, a gelled hydrofrac, they do slick water where they slightly gel the water, but they put in friction reducers, and they put in different things to basically make less friction occur so that the stuff gets into the fractures. Potassium chloride. They don't like to use fresh water. Fresh water actually causes the shales. These shales were laid down in the inland sea, very salty water. Now you put fresh water into a clay, it makes the clay swell. So they put potassium chloride so the swelling doesn't occur as much. Scale inhibitor. When they inject this stuff from the surface, it goes down, it's under great pressure. The ground is very warm. The ground temperature, ground and water temperature increases by about 1 degree centigrade, I believe, per 1,000 feet. So it's much warmer the deeper you go down. There's an interaction between the stuff that goes down, goes into the formation, and the formation water that's naturally there. What you push down is not what you get back out. So, what happens down depth, there's calcium, there's iron, and as you bring that stuff back out, it's cooler, there's less pressure, you start creating scale in pipes. You actually can start to create scale in the fractures, and that makes more friction, makes it more difficult for the gas to flow, and the scale in the pipes creates more friction inside the pipes, which you got to put more friction reducer in. There's biology in there. Sulfur bacteria, iron bacteria. You introduce that stuff into a fracture, it's like ringing the dinner bell. That bacteria will utilize the iron, the sulfur, whatever's available, and it secretes a mucus, and that'll block the fractures. So they want to kill the biology before it gets down there. The biocide is like a swimming pool chemical. Acids, a lot of calcium, you don't want that scale to build up. That's why the acid goes down. Friction reducers. All of the other stuff, that proprietary stuff, that's the stuff that has a lot of people concerned. They don't have to divulge it. In New York State has said, if you want to drill in New York State, you will tell DEC. DEC will not give that information to the public, but that information is divulged to the DEC. So if there is a problem, they can then, like a doctor at an emergency room, they can tell them, well, this is what's in there. They're going to sign a statement that they can't reveal it, so they can treat it. It's revealed to the state, but it doesn't go any further. But this is the general chemistry that goes down the hole. Now, what I tell people is, if this stuff is successfully pushed down into fractures that are created at depths of thousands of feet, you really don't have to worry about that getting back up to the surface. There may be one or two instances, but in general, what goes down there is like Las Vegas. What goes down there stays down there. Because once they start to produce the gas, they create a low pressure zone. That low pressure zone is what makes the gas flow out. You have a low pressure zone, any of that water that's there is going to flow back with the gas. It's not going to flow away from the well because of that low pressure zone created by the gas tube. So you've got this here. The problem is the transport of this chemistry to the site, the careful handling of it, the careful mixing of it, and the carefully getting it down the hole. The biggest concern is going to be bringing this stuff to and handling it on the site. This is where you're going to see surface water and groundwater contamination. The problem is, for every 1,000,000 gallons of stuff they use, they're bringing in, for 0.5%, they're bringing in 5,000 gallons of chemistry. If they do a 5-6 million gallon frac job, you're looking at, do the math, you're talking about bringing all this stuff safely to the site, carefully handling it, carefully mixing it, and carefully getting it down the hole. That's probably the biggest concern. Okay, what do we do with the flowback water and the formation water? From the SRBC, flowback water is that which is left over after they do the hydrofrac. The SRBC says, in general, for every 100,000 gallons they push down the hole, they get back 10 to 15%. The other 90 to 85% doesn't migrate away, it's trapped in the rock. This rock is dry. You're creating micro-sized fractures. Capillary action will hold a lot of that water, but as they start to produce the gas, that will come back out. That 10 to 15% is what comes back out of the hole. Once the flowback water is done, the rock at depth has brine in it, and that's called produced water. It's produced from the formation. Again, the Marcellus has a reputation. For every 1,000,000 cubic feet of natural gas produced, it produces about 200 gallons of brine.
What?
200 gallons per 1,000,000 cubic feet of natural gas. Not much. You go to the Barnett Shale, it'll produce 1,000 gallons of water, brine, for every 1,000,000 cubic feet of gas. You go to the Bakken, it's about 800. Each one's different. The Marcellus apparently is a fairly dry unit. But once that flowback comes, you again get the formation water, you got to do something with it. And that formation water, like I said, ain't Perrier. This is an analysis that we got from a well in southwestern Pennsylvania now 3 years ago. It was a 1.5 million gallon frac job. It was probably a vertical hole. Interestingly enough, in a 2-week period, they got it all back, plus interest. They apparently tapped into formation water. And the reason I say that, this is the first 500,000 gallons that came out of the hole, the second 500,000, and the third 500,000. Here, the chloride value is about 18,600 milligrams per liter. That's roughly seawater. By the time they got to the third 500,000 gallons, it's 5 times as salty as seawater. That's formation water. Things like sulfides. It's fairly low, it jumped up, and then it goes back down again. You look at things like barium. It goes from 668, that's not good stuff, to 6,100 to 8,700. This is part of the poor natural water quality that we have at depth. You look at other metals, they're not down there, they're not really produced. But the interesting part is that within the red box, this is called norm. This is not the guy at the end of the bar in Cheers. This is naturally occurring radioactive materials. When these shales were laid down as muds, hundreds of millions of years ago, there was a lot of natural uranium and thorium that was physically attracted to these organics. And that's the source of the radioactivity in the Marcellus. Again, you go to other units, they don't have as much, but the Marcellus does. Uranium and thorium has long half-lives. It breaks down over millions of years. One of the breakdown products is radium, 226, 228. 228 has a half-life of less than a week. 226 is several thousand years. Radium breaks down. It breaks down to radon gas. Now, each time it breaks down, it gives off alpha and beta particles. And that's the gross alpha and gross beta. So for the first 500,000, it's 1,100. Wow, it drops to 22. We're looking pretty good. And then it goes up to 19,000. This is the natural radioactivity that's in the brines. Drinking water standard. This is measured in picocuries per liter. Drinking water standard is 5. You don't take this stuff, you don't dump it on the ground, you don't try to dilute it in the stream, you got to get rid of it someplace else. You got to treat it, and you got to get rid of it. You don't mess with this stuff. But these are the general numbers, and this is one of the problems with Marcellus. It has a high radioactive content. And this is one of the concerns they have. What do you do with this stuff? 3 different types of suggestions. The first is deep well injection. Find a unit that's deep and inject it where there's high permeability. You go to any other shale and tight sand play in the United States, they have these units. They have units that are very deep, that have permeability, where they have injection wells, that they just inject this stuff. It's pushing it deep under the carpet. That's how they get rid of it. In Texas, it's called the Ellenberger sandstone. The joke I heard from a gas company was there's more injection wells in Texas than there are liquor stores. They have the aquifer that can take this fluid and it doesn't come back. I asked the company, where's it go? And they gave me this blank stare. It says, you're pushing stuff down there, it has to be going someplace. And he said, I don't know. More than likely it's probably going to the Gulf. But, you know, it's way down there, so out of sight, out of mind. New York State doesn't have an Ellenberger. We have the Potsdam sandstone. Up in Potsdam, it produced natural gas for a while. That Potsdam sandstone is thousands of feet below all these other gas-bearing members. But we don't have a good characterization. Can it take large volumes of fluid? We don't know. The Trenton Black River, remember I talked about the Graben features? One of the companies in southern New York drilled into one of these for gas, didn't find it. Said, well, let's test this for deep well injection. Didn't work. This will probably not work in New York. They're going to try, they're going to test, but I don't think it's going to work in New York. It doesn't, Pennsylvania has the same problem. They don't have the units. So what does Pennsylvania do right now? When they try to get rid of this stuff, they put it in tank cars, ship it to Ohio, where Ohio has aquifers that takes this stuff. So it's being shipped out of state. What will New York do? They may look at this. They probably won't, though, because these are the exact same units that they're looking for carbon sequestration. And they're finding it difficult to find these units to take the liquefied carbon dioxide gas. So this is probably not viable. Probably. This, you've probably heard about this in Pennsylvania, where they used wastewater treatment plants. These are wastewater treatment plants that are meant to treat human waste, not to treat industrial waste. But Pennsylvania early on said that in the western part of the state, they could take 20% of their discharge as flowback formation water. Simple concept. Solution to pollution is dilution. These things don't treat chlorides. These things don't treat radioactivity. they generally don't treat heavy metals. So a lot of these problems basically went right through the plant. Surprisingly, it didn't kill the plant, the biology in the plant, and went into a river. There are two or three of these along the Monongahela River. The Monongahela River flows north to the little village called Pittsburgh, and Pittsburgh uses the Monongahela River as its water source. They noticed an increase in the conductivity of the water. Several of the industries that use the Monongahela for cooling purposes were noticing scaling in their pipes. At that particular point in time, the Pennsylvania DEP blew the whistle, said time out. They said 1% of your discharge is flowback formation water. And then within the last 6 months, Pennsylvania strongly recommended that the industry not use wastewater treatment plants at all. And the industry said, okay. New York State has said if you meet certain criteria, you can use wastewater treatment plants, but only certain types. And those certain types are the ones that have what I call the black box. It's called industrial pretreatment. Industrial pretreatment can take out a lot of the chlorides, can take out a lot of the heavy metals, and with that, they take out a lot of the norm. They do this in Pennsylvania. But what they're finding is that they're getting this stuff out so it doesn't, so the water that's treated can then go through a wastewater treatment plant and then be mixed, assimilative capacity of the stream. But they're concentrating the heavy metals, the chlorides, and the radioactivity. That stuff goes through a filtration system, it's turned to a solid, they put it into a dumpster, they drive it to a landfill, sets off the radiation alarms, they check it off, it goes into their landfills. In Pennsylvania, they're allowed to basically deposit a certain amount of radioactivity in contained landfills, not in the construction demolition, but in the line part of the landfills. New York ships its medical waste out of the state. I don't think we'll see New York allowing landfills to take radioactive waste. I don't know for sure, but because they're shipping medical waste out of the state, this stuff is, quote, hotter. I don't think they're going to barrel. So it's a potential. It does work in certain areas. You concentrate, you create another problem. And the salt, in certain cases, they'll basically evaporate away the water, and they'll use that salt for de-icing. But they have to test it to make sure there's no radioactivity. They're looking at different ways of recycling and reusing. Okay, speaking of recycling and reusing, these are new concepts to reduce the flowback volume, and one of them is recycle reuse. Several of the industries are taking their flowback water. They're doing treatment on site, getting particulate matter out, and then they put that into a pond and they mix it with fresh water. Remember, only 10 to 15%, and it's ready to use in the next well. The produced water with the high salt, the high heavy metals, and the high, they can't. That's the stuff that gets shipped out of the state. So they are reusing and recycling the flowback water. And by the way, they're not being told to do this. The industry realizes that when they're working out in Montana and Wyoming and they're working down in Texas, there's nobody around, things were a little bit looser. In the Northeast, we got lots of trees and got people behind the trees. They realize they're between a rock and a hard place, and they are changing their recipes. They are changing what they're doing. They're looking to reduce the frac volumes. They're looking to get the volume that's going to go into the frac to fracture the rock, and then just put a water chaser behind it. So when they pump it back out, what they're getting basically out is pretty fresh water that they can reuse. Another thing they're looking at, you've got almost a mile-long piece of pipeline there. If the gas is under enough pressure, they just may take that water and put it back in the pipeline, let the gas bubble its way through. It'll produce it at the surface in time, but instead of having a big pot of water, they're going to be treating it over a long period of time. It's a possibility. Another one is to use liquefied gases, propane, carbon dioxide, and nitrogen. There's a company in Canada that uses this a lot, but they use it because they can. It's a shallow gas they're going after. If you get too deep, the propane and the other liquefied gases don't work that well. Sometimes they'll mix a water and a gas frac together. They're trying different experiments. They're trying to find something better. Halliburton now claims that they have a green frac fluid. In fact, if you check the newspapers, a VP at one of the meetings drank some. Ooh, it tastes like beer. Obviously, he doesn't have any taste buds. But they're touting that they have a green hydrofrac fluid. The recipes are changing over time. Hopefully, a year, 2, 3 years from now, This will not be a problem because the materials that they get down the hole and they get back out won't have these proprietary things that cause a lot of concern. They still have to deal with the formation water though. That's not going to go away. So bottom line, the industry wants to reduce it because they're being watched. Okay, local water resource concerns. This is stuff that we've sent to DEC last time and we're resending this time. Basically, we need to understand what goes on at gas well sites as they get there, as they drill, as they hydrofrack, and as they produce. And that data needs to be put on the web so you folks can see it. Not every well that's drilled is a Dimmick Township well. And not every well that's drilled is perfect. What it boils down to is a thing called relative risk. Easiest way I had to explain it. There's a relative risk of me getting a step ladder out here, moving this stuff out, and changing a bulb. Relative risk is small. The most engineered and safety-conscious project that the United States ever put together has had 2 major accidents and 14 people were killed. The space shuttle. Heavily engineered, heavily safety-conscious. We still had accidents. Marcellus falls somewhere between that. It's not always bad, it's not always good. There's a relative risk. I've worked on drilling rigs for over 30 years, not these big rigs, but I've drilled wells for monitoring wells. Accidents do occur. In talking to the SRBC, these guys are working with the gas companies in Pennsylvania. They told me that roughly 1 in 100 wells in Pennsylvania, in the Susquehanna Basin, has an environmental problem that needs to be cleaned up. They have to stop work and they have to clean it up, but it's not too bad. They say roughly 1 in every 300 to 400 wells has a major problem. Frac fluid, the one that occurred a couple of months ago, maybe 6 months ago now, where not at the blowout preventer, but at a flange below it, something happened and all that frac fluid went flying all over the place and it flowed into a stream and it caused some problems. Well blowouts. In one case, 2 drillers were killed. 1 in every 300 to 400 wells has a major problem. Again, not every well is going to have a problem, but not every well is going to be perfect. It's a relative risk. And I'm not here to tell you what that relative risk is. I'm giving you this information for you to make a decision. But there are these problems, but not every well is a Dimmick well, nor is every well perfect. Just keep that in your mind. What is the relative risk? There's a relative risk for me driving to work every morning. I go to work at 5 o'clock in the morning, and my son claims I've killed more deer with my truck than most people have killed with their rifles. The truck I have right now, I've killed 3 deer, and I had 3 run into the truck about 2 weeks ago. There's a relative risk in everything we do. Okay, regional, this is more scientific. We don't have a good understanding. Remember I said that things are different across the plate. We need to understand this. We need to understand this not only for you folks, but also for scientists and also for the gas companies. So we need to understand all of this. We have proposed to put together a regional Marcellus database where we report this stuff out to the public. Everybody says it's a good idea, but unfortunately we live off of soft money, somebody's got to pay us to do it. So we have good intentions. Okay, once you drill it, you got to transport it. Now, remember all those wells I showed you, those permits in the southern tier? There's a pipeline that goes through there. It's called the Millennium Pipeline. It's a major transportation pipeline. Initially, they're going to drill wells where they're close to pipelines. As they start to understand where the sweet spot is, where they're going to develop gas, we'll then start either using other pipelines or we'll start to expand new pipelines out in those areas. In Pennsylvania right now, they've drilled so many wells that they've used up the capacity of the pipes in Pennsylvania to transport the gas. Now these companies are saying, we want to put another pipeline next to the pipeline we have to transport this gas. So right now in Pennsylvania, a lot of these companies have capped their wells. There's no place to push it. If there's a sweet spot in New York, we may see something similar. Because the Millennium is the major one. There's the Tennessee, and there's a whole bunch of other ones. On the way over here today, I saw at least one new pipeline that was built, probably in Delaware County. You drive down into Pennsylvania, I do a lot of driving down to Penn State. There's new pipelines going across hills all the time because there's so much gas being produced. Now, this is one of the big things. It's called Article 23 of the Environmental Conservation Law. This is currently being fought in municipalities and possibly in your municipality. The New York State Environmental Conservation Law 23 states in yellow, New York's oil, gas, solution mining law specifically supersedes all local laws or ordinances related to the regulation of oil, gas, solution mining, and brine disposal, but reserves the local government's jurisdiction over local roads and the rights of local governments under real property tax law. Basically what it says is you can't regulate out gas well drilling. There's a number of communities in central New York who have said, oh yeah, here's our rules and regs. Right now, Anschutz, the gas company, is suing the village of Dryden, New York, or town of Dryden, New York, on their law to prohibit gas well drilling. Other municipalities have said we have a zoning regulations against industrial processes. They don't name hydraulic fracturing or drilling. So the gas industry is going after Dryden because it's specific to the gas industry. Again, DEC is doing what they're told. You may not like it, and some of them don't like it, but that's what the rule is. The rule needs to be changed. So you folks need to become active. If you're for or against, you need to become active. These are just some of the general things. A municipality can use, as far as road use, can bond their local roads. In order to do that, they need to understand what their roads are. If there's a culvert underneath Legion Road right here that can only handle 15 tons, and these regs are 30 tons, the town can say you can't drive this road unless you want to go out there and replace the culvert and make it so you can take 30 tons across it, or a bridge or anything like that. They can, your municipality has control over local roads. You can tell them during school hours, no trucks out. Our kids are important. They can do that. You can tell them you can't drive after 10 o'clock and not before 6. Things like that. You can regulate the use of your roads. You can tax the value of the gas. Your tax auditor doesn't have to put on the green visor and calculator. The New York State Office of Real Property Tax Services does that for them. All your local town has to figure out is how much gas was produced. You charge school tax, county tax, village tax, whatever. That can be done. You can regulate to a degree the location of new wells. You do that with DEC. You know, regulated wetlands, basically agricultural districts, water supplies. It basically is another hoop to go through in the secret process. You can regulate the use of municipal water. If your gas company says to Jeffersonville, we want to buy your excess capacity, and if you got it, you can sell it, or you can say no. Simple as that. And they can approach you with your wastewater treatment plant. You can say yes, or you can say no. You can basically regulate the disposal, road spreading of brine. Believe it or not, New York State still allows formation water, not flowback water, but formation water. They allow it to be spread on roads. It does have a heavy metal content. Generally, most of the formation water is not Marcellus. In fact, none of it is now. It doesn't have radioactivity, but it has heavy metals. You can tell them, yes or no. And you can follow up with the oil and gas companies in as far as if there's a problem with somebody's well goes bad. Right now, the county health department, lacking that, the state health department will come in, will investigate Farmer Brown's complaint, and can say, these guys caused this problem. This is another comment that we're sending to the state. In New York, the homeowner has to prove that they caused the problem. In Pennsylvania, the burden of proof is on the gas company. It's an old mining rule that the mining company, if they cause a problem, have to prove that they didn't despoil this water well. So it's a difference in states. I was hoping I was going to see that change in the revised SGIS. It's not there. So you can follow up after the health department makes a determination. But Article 23 limits what a municipality can do. If you don't like it, get the legislation changed. Questions?
A couple of questions. How thick is the cement? How thick?
In general, it has to be, I believe, 2 inches, if not more. So if they drill a 36-inch well and put a 30-inch casing, that means there's 3 inches around the outside.
Right. My basement is about 10, and I sometimes get a leak in my basement, and that's at surface.
Yeah, there is a concern about the grouts. The grouts are specifically produced. In certain cases, they're expanding grouts so that they fill all these nooks and crannies. In certain cases, if there's a lot of pressure, they'll pump in at great expense what's called a thixotropic cement. It sets in about 20 minutes.
And how long do they last?
That's a good question. There's general information out there that these cement grouts don't last forever. Nobody's ever measured forever. In certain cases, they may fail within a couple of years. They may fail within 20 or 30 years. We don't have a long-term history, nor has anybody really studied grouts in gas fields for a long period of time. I do know that out west in, I think it was Utah, USGS has a program where they're going around and they have a soil sniffer and they go around to old wells that have been cut off and there's methane coming out of the ground. Were they properly grouted? We don't know.
One other question, you talked about how there's a major problem statistically with every 300 or 400 wells. What is the overall total of wells that can be anticipated in New York State once this gets started? If it's 20,000, you divide by 400,
Right.
How many problem wells do you
Right.
have?
Realize, number one, that I believe the number, don't quote me, but I think the number projected is 60,000 wells across New York State.
Quake tremor that came up from
Virginia.
West Virginia, and right up where there's been wells drilled. Has there been any research at all as to any fracture of the casings?
To answer that question, for the Virginia earthquake, no. But in California, where there are a lot of oil wells, and they have a lot of earthquakes, a lot more than we have here, the track record there is when they've had the San Francisco earthquake, which was I think a 7.8 or something like that. Out of all the oil wells that were in California, there was a handful, I don't know the number, of wells that did develop problems that they went in and fixed. No well casings were sheared, but grout seals were broken.
Part to that question is, how many cases of water well contaminations have there been?
It depends. There have been water well contamination problems. I know of a number of them. A lot of them occurred before DEC started regulating oil and gas drilling. They started in the 60s. The rules, the GEIS came out in 1992. So between 60 and 92 was when DEC started to regulate. There have been instances of water well contamination in the past. In one case that I know of in western New York, because I was working out in the western part of the state, they were drilling down. They had yet to set a surface, they set a surface casing. They were going to do the intermediate casing. They had an open hole. They drilled through the Marcellus into the upper Onondaga. They hit what's called a reef structure. It was a Friday afternoon. They tried to bring a company up to kill the well, basically fill it with cement. They couldn't get it there. The well was venting tremendous amounts of gas. Don't know whether it was made in the field or in the main office. They said shut in the well. They let the well pressurize. The well did pressurize. It wasn't cased. The gas flowed out through the unconsolidated material and ended up about a quarter or half mile away, coming into people's basements and percolating up into a stream. They did the wrong thing.
But let's say your neighbor across the street or down the road has leased his land out, he has, let's say, 110 acres. So I'm concerned about my water, I'm halfway up the road.
Right.
What are the toxic implications, which
New York State has made recommendations that from the well path, they need to go out 1,000, if not 2,000 feet out, and knock on your door and say, I'm going to be drilling a well across from your house, and I'd like to test your water. It's up to you to say yay or nay. If you say nay, you're doing yourself a disservice. Let them come in and test your water. If you don't believe them, what you can do is you can hire somebody that's going to represent you and say, okay, I want you to come in next Wednesday when I have my person here, and we'll do a split sample. It's going to cost you. Or the other way, they're going to do the test and they're going to give you the results. If you don't believe them, you have the right to either say no or to say we'll do a split sample.
What are the chances of it affecting your water? Pretty good, right?
If I knew, I'd be in Las Vegas right now. The potential, again, is going to be more probably of a surface water contamination that gets in the groundwater than a deep hydrofrac with that fluid coming back up into your well. So certain companies line their entire well pad, and they drain it all to one point. So, stormwater goes to one point. If there's a spill, it goes to that same point. They collect it, they treat it, properly dispose it.
What happens after the well is finished, it's dried, or done, to the property afterwards?
Okay, are you talking about while it's producing or after it's done?
After it's all done, they've got the gas out that they can, they cap the well, they go away.
Well, they
What's
don't
the
cap
value,
it.
or whatever they do to the
They're
well?
required to do what's called plug and abandon. They're required to go down into that well and at the far end of the well start, just like they were doing with the casings, start injecting cement and inject cement and seal that well all the way back up to the surface. The well pad itself, generally if it's going to be a multi-well pad, they say it's going to be 3 to 5 acres in size, depending on the number of laterals going out. Generally, once they're done, they probably won't need all that area. They're going to have what are called Christmas trees. They're going to have wells with valves on it. And then they're going to have a separator that's going to separate the gas from the formation water. And then they're going to have brine tanks. Truck's going to show up every so often and drain those brine tanks, and they're going to take that brine and treat it someplace and dispose of it. So you may go from 3 to 5 acres to maybe 2 to 3 acres. That 3 to 5 acres, remember I said there are Uticas down there? They probably won't let it go back to vegetation, forest vegetation. They may come back and they may reutilize that pad to drill another set of wells that go down to the Utica. Don't know. We don't know their production capability. We don't know enough about the Utica to say, yeah, they're going to do it here, and no, they're not going to do it here. So the potential is 3 to 5 acres, be smaller during production. Once they cap the wells, I believe that if they cap the wells, they then reduce the size that much more, so you still have the well pad around the wells proper, just for inspection purposes.
I'm concerned about the floodplains, and that's...
New York State has a certain set of rules about the floodplains. No open pits whatsoever. Everything has to be containerized. I actually thought about this on the drive down because I knew somebody was going to ask the question because of the floods we've recently had. I do not believe they are prohibited from drilling on the floodplain, but they are very strict rules about what they can and can't do on a floodplain. Go to War and Peace, number 2. I will check because, like I said, I was trying to remember and I couldn't remember. But the rules have been made more strict about drilling them.